Welcome back, student. Now, today we'll discuss about pressure losses in duct. In the previous lecture video, we already discussed that what is duct, what is the main function of duct, and what is the duct material, what is the duct shape and construction, and all these things already discussed in the previous lecture video. Now, in this lecture video, we'll discuss about the pressure losses in duct and pressure losses in duct due to friction, due to various type of dynamic losses. Okay, means pressure losses due to the bending, due to the construction, due to the bending or arrangement. So these are the pressure losses we can discuss about this, and obviously the equivalent diameter of the circle for a rectangular duct. Okay, and we already discussed all these things. Now, now pressure losses in duct. Pressure losses in duct when in a duct through a particular when through a duct the air is flow, means air conditioning air flow through a duct. There are some pressure loss. Pressure loss due to the friction between the moving particle of the fluid. Moving particle of the fluid means air. Moving particle of the air and the interior surface of the duct. So this is called basically friction loss. So friction loss basically occurs due to the friction between the moving particle of the air or fluid and the interior surface of the duct. That is called basically friction loss. And dynamic loss is basically the pressure loss due to the dynamically at the changes of direction. At the changes of direction, suppose if the duct is flow through a particular straight line, then if it is a bend or 90 degree or 45-degree angle like this channel, so obviously there is some change in direction. So due to the direction change, that there are some pressure losses occurs, and this loss basically called dynamic loss. Okay, now due to the friction, what amount of pressure loss occurs, we can calculate from the DRPN formula, that is PF, pressure loss due to the friction, that is equal to FL divided by FL into rho A into V square divided by 2M, where F is your friction factor, L is your length of the duct, rho A is your density of air, that is 1.2 here, and V is the velocity of air. Now M, what is M? Main question is what is M in this equation. So M basically hydraulic mean depth. So hydraulic mean depth in meter, which is the ratio between cross-sectional area of duct divided by weighted perimeter of the duct. So A by P. Now this equation can also written this equation can also be written as in this form, that PF is equal to FL by M. So FL by M into rho A into V square by 2, which is nothing but PV, as we discussed that what is static pressure, dynamic pressure and total pressure. So dynamic pressure basically PV, and that is equal to rho A into V square by 2, where rho A is basically your density of air, V is the velocity. Okay, now PV is basically V by 4.04 the whole square millimeter of water. Okay, so PV is equal to V by 4.04 the whole square millimeter of water. Now in terms of that, FL by M into PV mm of water. Okay, so in terms of PV, you can write here that V by 4.04 the whole square millimeter of water. Okay, so PF, okay, so PF is equal to FL by M into V divided by 4.04 mm of water. So it can also written as either direct formula, PF is equal to FL rho A into V square by 2M, or it also written as FL by M into V by 4.04 the whole square millimeter of water. Now as you know, because PV is equal to this one, already discussed. Okay, now if when the air is basically at a temperature of 3 degrees Celsius, if the air is flow through a particular channel or duct, now temperature of the air is suppose 3 degree or 20 degree, 30 degrees Celsius, then the pressure loss due to the friction, you can calculate that PF is equal to FL by M. So FL by M into V by 4.04 the whole square into 273 plus 20 divided by 273 plus that amount of temperature of the air which is exist within the duct, that is 270 plus T millimeter of water. Okay, so this is the pressure loss due to the temperature when the air temperature is known that T degrees Celsius. Okay. Now one more question to you, that hydraulic mean depth. You know that hydraulic mean depth, that is M, that is ratio of cross-sectional area of the duct divided by perimeter. So A by P. So A by P, basically your M is equal to A by P. So that will be for the circular duct, M is equal to D by 4, and for rectangular duct, M will be is equal to AB divided by 2 into A plus B. So this is the hydraulic mean depth for circular duct and rectangular duct, because as we discussed that the shape of the duct, that is basically either circular, rectangle or square. Okay, there are some advantage and disadvantage in between circular duct, in between rectangular duct or square duct, but when you calculate the hydraulic mean depth of circular duct, M is equal to D by 4, and similarly for rectangular duct it will be M is equal to AB divided by 2 into A plus B. Okay, now time back to the next topic, friction factor for duct. So friction factor, because pressure loss due to the friction, that is Pf, that is equal to F into L into rho A into V square by 2F, where F is your friction factor. Okay, now what is the friction factor for the duct? Now it depends on the type of flow. As we know that flow is basically the two types, the laminar flow and turbulent flow. As we know that it is depend on the Reynolds number, if it is a laminar flow, turbulent flow, because if the Reynolds number value is less than 2000, then it is called basically laminar flow. If it is greater than 4000, that is called turbulent flow. Now you can calculate the Reynolds number for corresponding air condition. So that is Reynolds number is equal to rho into V into D, means rho is the density, V is the velocity, and D is the diameter. Okay, so diameter of the pipe or duct. So mu is your dynamic viscosity. Okay, so if you put all this value, you can get the value like either 2000, 3000, 4000. So depending on that the value, you can say that it is a laminar or turbulent flow. So for the laminar type of flow, the friction factor will be F is equal to 64 by Rn. So put this value here compared to the Rn, that is 64 by Rn, you can get your friction factor for the laminar flow. And for turbulent flow, F is equal to 0.3164 divided by Rn to the power 1.5 or 1 by 5. So that will be 0.25. So if you get values, if you know the value of Rn, so you can easily calculate the value of F is friction factor for the turbulent flow. Okay, so this is the friction factor for duct, for normal, for laminar, turbulent flow, and in some cases, if the duct is basically in rough surfaces, then the friction factor, it depends on various surface roughness, all these things. So we can discuss on that. Okay. Now, friction factor for duct. As you know that the friction factor for laminar flow and turbulent flow, the friction factor for laminar flow, that is basically 64 by Rn. Okay, Rn basically your Reynolds number, which is depends on Reynolds number. It is a laminar flow or turbulent flow. Now, for the friction factor for the duct, if the duct is rough, then the friction factor will be, because that depends on the roughness factor, which is the ratio of E by D, small e by D. Now, small e is your absolute roughness of the surface, and D is your diameter of the duct. And now friction factor for this case, actually for rough duct, the friction factor will be 1 by 1.74 minus 2 log into 2e by d the whole square. Now this can be also calculated from the Moody's chart, where the friction factor is drawn with the Reynolds number as well as relative humidity. We can see that. So in this diagram there are various lines in your chart. If you see your book, you can see that there are Moody's chart up there, and in which you can get idea about the friction factor, which is basically a diagram with respect to Reynolds number as well as relative roughness. Okay. Now the next topic is equivalent diameter. Equivalent diameter of a circular duct for a rectangular duct. Equivalent diameter of a rectangular. Equivalent diameter of a circular duct for a rectangular duct. Now you have to calculate the same equivalent diameter of the circular duct for a rectangular duct. Okay. Now there are two cases, maybe there are possible. There are two cases. First, if the condition is that when the quantity of air is passing through the rectangular and circular duct is same, means amount of air is flow through a particular duct in rectangular duct and circular duct, both are same. That means Q is same for both the duct. Okay, if it is follow this equation, follow this condition, then you can apply that. You know that quantity equation or rate of discharge. Okay, now you know that Q is equal to A into V. So from that expression, you can calculate the velocity of air which is passing through a circular duct, that is Vc. That is basically Q by AC. So as you know, the Q is equal to AC into Vc. For the circular duct, AC means the cross-sectional area of the circular duct, and Vc is the velocity of the circular duct. Okay. Now, velocity of air actually in the circular duct, and velocity of air in passing through a rectangular duct, that is basically VR. VR will be Q divided by AR. AR basically cross-sectional area of the rectangular duct, and VR basically the velocity of air in a rectangular duct. Okay. So VR is equal to Q by AR. Now, as you know that the friction factor means pressure loss due to the friction, that is basically PF is equal to FL into rho A into V square divided by 2N, where F is the friction factor, L is the length of the duct, rho is your density, and V is the velocity, and M in that equation, that is basically hydraulic mean depth. So M is basically the ratio between the cross-sectional area of the duct divided by the perimeter of the duct. Okay. Now, you know that in terms of here, that is here V. So if you put this here VC or VR, so you can write in terms of VC or VR, right? So it will be written as in this form also, FL rho A divided by 2N into V square. So V square, it will be written as Q by A, because Q is equal to A into V. So V is equal to Q by A the whole square, because this is equal to Q by A the whole square. Okay. Now, if you write these equations this way, that pressure loss due to the friction. Now you have to calculate the pressure loss, because you know that the pressure loss due to the friction, that is basically FL rho divided by 2M into Q by A the whole square. Okay. Now pressure loss due to the friction for circular duct, PFC, it will be that FL rho A by 2 into M. M is basically hydraulic mean depth, that is the ratio between A by P, means cross-sectional area divided by perimeter. Now in terms of M, here M is equal to A by P, so it will be P by A, so PC by AC here, and it will be Q by A the whole square. Similarly for the rectangular duct also, it will be written as same, just it is different with that here it is PR by ARQ. Okay. So as you know that all these terms, so in this term actually in this expression, FL rho A into Q the whole square, and in this expression for the rectangular duct, that is FL rho A into Q. Rho is the friction factor, which is basically same. A is length of the duct, which is a constant, and rho is the density of air, which is constant also for the density of air, and Q is the discharge, because we have firstly assumed that the quantity of air passing through a rectangular duct as well as circular duct is same, so Q is same. So all this term in this expression is same, just the difference is that PC by AC the whole Q and PR by ARQ the whole Q. So it will be equal. So if PC by AC the whole Q, I'm sorry, it will be C by AC the whole Q, PR by A. Okay. Now, you know that the PC basically the perimeter of the circular duct, AC basically cross-sectional area of the circular duct. Okay, and PR basically perimeter of the rectangular duct, and AR basically cross-sectional area of the rectangular duct. Now, if you put all these values here in terms of PC and AC, PR, AR here, you can get that for the circular duct of the perimeter, that will be pi into D, and cross-sectional area of the, if the diameter of the duct is basically D, then pi by 4 into D, D square to the power whole cube. Okay. Now for the rectangular duct, the perimeter will be 2 into A plus B. A is your the length and B is the width, and here it will be a cross-sectional area, that will be A into B. Okay, the whole cube, because A are the whole cube. Okay. Now if you calculate this, you can get 32 by pi square D5. Okay, pi square D5 into A plus B divided by AQ plus BQ. Okay. Now in terms of that, here you have to calculate the equivalent diameter. That means you have to calculate here in this diameter only d is here, so you have to calculate this diameter in terms of all this expression. So d5 it also written in this form also here. So d5 it will be 32 into a cube bq divided by pi square a plus b. So d to the power 5 here you have to calculate only d. So d to the power 1 by 5 will be on that side. So 32 into a cube bq divided by pi square into a plus b to the power 1 by 5. If you get this value, if you do the calculations, that d will be, that means diameter of the equivalent diameter of the circular duct, that will be d, that will be 1.265 into a cube b cube divided by a plus b to the power 1 by 5. So this is your equivalent diameter of a circular duct for a rectangular duct. Okay. Now, we want to discuss that equivalent diameter of a circular duct for a rectangular duct. The condition was that in the first case, that we assume that the quantity of air that passing through the say rectangular duct as well as circular duct is same. That means Q is same throughout the rectangular duct as well as circular duct. For that case, we calculate that the diameter. We will calculate the diameter of the duct, that is D, or D is equal to 1.265 into AQ BQ divided by A plus B, to the whole to the power 1 by 5, where A is your longer side of the rectangular duct, B is your shorter side of the rectangular duct. If the rectangular, as you see that the duct can be rectangular shape, circular shape or square shape. If it is rectangular square shape, if it is rectangular shape, then obviously there will be some longer side, that will be A, in the shorter side that will be B. Okay, and if it is a square duct, obviously A is equal to B in that case. And if it is a diameter, if it is a circular duct, so obviously for that particular duct, this type of duct, actually you have to require the diameter for the circular duct. Okay, as we discussed, and we already calculated that D is equal to 1.265 into A cube B cube divided by A plus B to the power whole to the power 1 by 5. So this is the equivalent diameter of a circular duct for a rectangular duct. Now, when the velocity of air that passing through the circular duct and as well as rectangular duct. Now, when the velocity of air means when the air is flow, means condition air from the air conditioning equipment to the room or spaces where to be air conditioned, the velocity of that particular air is, if the velocity of air is basically constant throughout the duct, then you can write that if this condition is satisfied here, then, and if you know that the friction loss due to the means pressure loss due to the friction, that is PA, friction loss due to the pressure loss due to the friction, that will be PF, that is equal to FL rho A into V square by 2m, where F is the friction factor, N is your length of duct, rho is your density, V is the velocity of the duct, the velocity of the air, sorry, and M is the hydraulic mean depth. Okay, hydraulic mean depth, which is the ratio of cross-sectional area of the duct divided by perimeter of the duct. Now, in terms of M, we can write here, here M is equal to A by P. So written as P by A here. Okay, PF is equal to in this form. Now, if you know that PF is equal to this one, then if you calculate the PFC, means pressure loss due to the friction in circular duct, that is PFC, that will be FL rho A V square divided by 2, because V is your constant in circular duct as well as rectangular duct, into PC by AC. Okay, similarly for the rectangular duct, that is for pressure loss due to the friction for rectangular duct, that will be FL rho A V square by 2 into PR by AR. So in both this equation, PFC and PFR, so both the expression, what you see that FL P rho A into V, FL rho A into V, because this is a friction factor, both these for the same velocity of flow, the friction factor is same, because friction factor somehow related with the Reynolds number. Reynolds number somehow related with the velocity of the fluid. Okay, so that's why F is the friction factor, which is same. L is the length of duct is same. Rho is density of air is same, and V is the velocity, which is assumed that with the velocity of air is passing through same. So both this quantity is same for PFC, for PFR. Now, if 2 is equal, these to be equal. Okay, so PC by AC is equal to PL by AR. Okay. Now you know that this is your perimeter of the circular duct, that is pi into d. This is the diameter of the circular duct, and is your cross-sectional area of the circular duct. If d is the diameter of the circular duct, then the cross-sectional will be pi by 4 into d square. Okay. Similarly, for PR it will be 2 into a plus b divided by AR is equal to a into b. So from this expression, you can calculate that d. Okay. So if you calculate that d, it will be that b is equal to 2ab into a plus b. It will be 2a divided by a by b plus 1. So a is basically your longer side of the rectangular duct and b is your shorter side of the rectangular duct. So the equivalent diameter of a circular duct, that d, it will be 1.265 into a cube b cube divided by a plus b whole to the power 1 by 3, when the quantity of air passing through the circular duct and rectangular duct is same, and when d is equal to 2ab divided by a plus b, or 2a divided by b plus 1, where a by b is basically your aspect ratio. Okay. And when it will be followed when the velocity of air passing through the rectangular duct as well as circular duct is same. Okay, so this is the equivalent diameter of a rectangular duct, and for as well as circular duct, and there are some pressure losses due to the dynamic losses. Actually, we can say that this type of losses is dynamic losses, because when the air or air conditioning airs flow through a particular duct, there are some arrangement, there should be such arrangement that there are some direction change. Okay, the airflow direction will be changed in, simultaneously. So what happened that due to the direction change, the bending or the 90 degree, if their construction features such that the duct are in the 90 degree or 45 degree or bending in construction, then there are some losses occurs. Okay, this type of losses are actually uh, uh, this type of losses actually called dynamic loss. It may be happen due to the contraction, even when the duct are in this set, this is called contraction. If the duct is in this way, that is called enlargement. So in this way, actually, there are some pressure losses occurs due to the bending, with the 45 degree angle, the contraction, expansion, sudden enlargement. Because I think all of you have give some idea that some pressure losses due to the fluid, okay, due to the bending, due to the sudden conduction, sudden enlargement. So all these things will be same in this also for the duct system. So go through this. Okay, so thank you very much for listening and watching me, and goodbye.